Welcome. Today we will try to explore the complex numbers through some examples. To begin with, we must know the concept of complex conjugate. It is defined for a complex number z equal to x plus iy as z bar or z star in some books, and is given as x minus iy. So we have to change the sign of the imaginary part. That thing we have to remember. Now, if somebody asks, what is the complex conjugate of a real number? Say z equal to 2. So we have earlier seen that this can be written as 2 plus 0i. So its complex conjugate will be z bar equal to 2 minus 0i, which is same as 2. So a real number is complex conjugate of itself. As an example, let us try to represent a complex number z equal to minus 1 minus I in both of the familiar forms. If we recall from our previous lecture, z, which is usually represented as x plus iy, which is also represented as r e raised to I theta, with the relations given as r equals root of x squared plus y squared and theta being equal to tan inverse of y by x. Okay, so we will use these formulae, and we will also try to represent this number graphically. So if we compare this with the standard form, we get x is equal to minus 1 and y is equal to minus 1. Fine. So we can directly go and write r equal to root of minus 1 squared plus minus 1 squared, which is root of 1 plus 1. So r equals square root of 2. Now what remains is to find out the value of theta, which is slightly tricky because even though we have a formula for theta, theta is preferably to be found out using graphical representation, because remember, theta is always measured with respect to positive x-axis in anti-clockwise direction. So we'll try to represent this number z equals minus 1 minus I on a graph. So we can draw x and y axis, xy. Remember that this belongs to real part, this belongs to imaginary part. So minus 1 will be here for x, since x and y both are minus 1. And minus 1 on the y-axis will be here. So our number with coordinate pair minus 1 will be in the third quadrant. Now this is r, and now according to the definition of theta, which is mentioned here, theta will be this much. Now we can see the problem with this formula. The formula which we have learned will give us as different value because if we look closer, this is the point of interest, -1 -1. The formula which says tan inverse of y by x is nothing but theta will give us this particular value of theta. Let's call it as some theta dash. But in our case, we are interested in the other value theta, because theta is always measured with respect to positive x-axis in anti-clockwise direction. So if we call this as theta dash, clearly theta dash would be tan inverse of -1 upon -1, which is tan inverse of 1. So this would be just pi by 4 or 45 degrees. But remember, we are going to take the value expressed in radians. So theta which we are interested in would be just pi by 2 plus pi by 2 plus theta dash. So pi by 2 plus pi by 2 plus theta dash, which would be pi plus pi by 4. So final value of theta would be 5 pi by 4. Yes. Now there is another concept to this. This is mostly called as principal theta. And why is it so? Because suppose that we are having a particular direction of r given by a value of theta, we can come across the same position by repeating an entire cycle, either clockwise or anti-clockwise. So we can reach the same location. We can reach the same location by adding or subtracting any integral multiple of 2 pi to this value of theta. So theta in fact has infinitely many values. Infinitely many values. So we can just add or subtract any integral multiple of 2 pi, or in other way we can say that theta plus or minus 2n pi, with n taking values -3, -1, 0, 1, 2, 3, and so on both the sides. Fine. But we will right now consider the principal value of theta as the required value. So we have with us x equal to -1, y equal to -1, r equal to root of 2, and theta equal to 5 pi by 4. So yes, we have represented the number graphically, and z is now, if we recall, can be written as root 2 e raised to I 5 pi by 4. So this is how we can represent the same number in polar form by taking help of diagram. Let us take another example, make it clear. Suppose z equals 2i. Z equals 2i. Now clearly, if we compare this with x plus iy formula or expression, in this case z equals 0 plus 2i. So this means x equals 0 and y equals 2. This is a special case where the z is completely imaginary with no real part. So obviously, if we try to represent this, x coordinate would be 0, coordinate would be 0. y coordinate would be 2. So the number belongs to y-axis. Clearly, r is a straightforward relation. 0 squared plus 2 squared, which is 2. How much would be theta? No need to calculate. We can directly see from the graph that theta is going to be pi by 2. So the same z, which is 2I in Cartesian method, is now 2e raised to I pi by 2. So this is the way how we convert between Cartesian and polar forms with the help of a diagram. Let us move forward. Now, let's try to understand how we can express any complex expression. How we can express any complex expression always in the familiar form. Always in the familiar form. For an example, we will try to see what comes for this particular 1 plus I bracket squared. We have to solve this using the well-known function a plus or minus b bracket squared equal to a squared plus or minus 2ab plus b squared. We will apply this formula to get 1 plus I bracket squared equals 1 squared plus 2 into 1 into I plus I squared. So this is 1 plus 2I, and remember that since I was defined as square root of minus 1, I squared is going to be minus of 1. So let us substitute here minus 1, which gives us just 2I. So yes, 2I is 0 plus 2I is nothing but the required expression. So in principle, any complex expression can be always simplified to the x plus iy form, and further this can also be converted into the polar form r e raised to I theta. We can also try doing that. If we see that this 0 plus 2I gives us x equal to 0 and y equal to 2. We have already done this task here. 2e raised to I pi by 2. Now we will take another example, which will be z equal to 2 plus I upon 3 minus I. Now, in order to solve this expression or simplify this expression, we will need the concept of complex conjugate. Complex conjugate. A common trick to simplify this expression would be multiply and divide by the complex conjugate. Let us write it in short as CC. Multiply and divide by the complex conjugate of the denominator. So z will be 2 plus I upon 3 minus I into 3 plus I 3 plus I, right? So we have multiplied and divide by the complex conjugate of the denominator. So this becomes 2 plus I into 3 plus I upon, now here we are going to apply another formula which tells us that a plus b into a minus b is a squared minus b squared. This will be 3 squared minus I squared. In the numerator part we have to multiply the things. So 2 into 3 is 6 plus 2 into I is 2I plus 3 into I is 3I plus I into I is I squared, whole divided by 9 minus of minus 1. Remember, again we are substituting minus 1 for I squared. So this will be 6 plus 5I plus I squared is minus 1, and 9 minus of minus 1 is 9 plus 1, which is 10. So this is further simplified to 6 minus 1 is 5 plus 5I by 10, which gives us 1 by 2 plus 1 by 2I. Yes. So this is again the familiar form of x plus I. So what was our previous original expression? 2 plus I by 3 minus I. So 2 plus I by 3 minus I is equivalent to half plus half I. So yes, we again have simplified a complex expression to a familiar, well-known form. Thank you.